James Webb has now confirmed a galaxy we see as it was only about 280 million years after the Big Bang. If you picture that as another step toward the edge of the universe, the picture is understandable. But MOMZ-14 is not an edge in space. It is a frontier in what has reached our instruments. And tonight we can follow that difference through the oldest light, the observable horizon, and the geometry of the whole universe, to ask what any of them can actually tell us about the size of the whole universe. The image itself is modest, a small yellow blur in a deep field crowded with other distant points, easy to miss without the label beside it. Its importance comes from when that light began its journey. Webb is receiving a message from an early stage of cosmic history, and the fact that the message is extremely old does not turn the source into a wall at the end of space. A telescope can move the frontier of what we have observed without discovering a physical border, because the limits of observation depend on more than the size of a mirror. Time, expansion, the transparency of the early universe, and the causal structure of space-time all place different limits on what can reach us. NASA describes Webb as the largest telescope ever launched into space, and its infrared instruments were built to collect faint light from the early cosmos. As the universe expands, ancient light is stretched toward longer wavelengths, so radiation that left a distant source at shorter wavelengths can arrive in the infrared. Webb was designed to measure that red-shifted light. Webb has carried galaxy observations deeper into cosmic history than earlier telescopes could confirm spectroscopically. MOMZ-14 has a measured redshift of 14.44, and NASA reports that its light traveled for about 13.5 billion years before reaching us, placing the source in the universe's first few hundred million years. And yet that frontier is not the same thing as an outer border. Webb has reached an observational frontier, while the total extent of space remains a different question. Imagine standing on a shoreline at night with a lantern. A brighter lantern lets you see more water, but the farthest visible point still tells you about the reach of the light rather than the size of the sea. A telescope faces a more complicated version of the same problem because its reach is limited by sensitivity and by the history of the light trying to reach it. Now replace the lantern with a space telescope, the water with the history of the cosmos, and the darkness with the limits imposed by time, expansion, and the behavior of light itself. That is closer to the situation we are in. If you are listening in the dark, the easiest picture is a sphere with a final surface, somewhere beyond the faintest galaxy. Astronomy has trained us to draw maps that way because a circle or sphere is convenient on a page. But the sphere around an observer is usually describing access to information, not a photograph container around all existence. That difference will keep returning as the scales grow. The way MOMZ-14 was confirmed already shows the distinction. The image tells astronomers where the faint source appears on the sky, while spectroscopy spreads its light by wavelength, so recognizable features can be compared with where those features are expected to occur. Their displacement gives the redshift, and a cosmological model connects that redshift with an era in the expanding universe. Each step is a measurement or an inference from arriving light. None requires a view of the universe from outside. The instruments divide that job in a useful way. Webb's near-infrared camera can reveal a faint candidate and measure its brightness through different filters, which gives astronomers an initial estimate of how strongly the light may have been redshifted. The record becomes firmer when the near-infrared spectrograph separates the light into a spectrum and lets the team locate features whose expected wavelengths are already known from atomic physics. For MOMZ-14, that spectroscopic step fixed the redshift at 14.44. The distinction matters because an image can tell us that a source is worth investigating, while a spectrum can place that source much more securely in cosmic history. Neither measurement is a ruler laid across the entire universe. Both begin with the small amount of ancient light that actually arrived at Webb. This also means that the word limit will change meaning as we go. One limit belongs to an instrument because a detector has finite sensitivity and a defined wavelength range. Another belongs to the history of electromagnetic light because the early universe was once opaque. A still larger limit comes from causality, because signals need time to cross an expanding cosmos. Those limits can sit in the same conversation without being the same boundary. That is why a record-setting galaxy can be both genuinely important and easy to overread. It moves one frontier farther into cosmic history. It does not tell us that space ends immediately beyond the source, and it does not tell us whether the total universe is finite or infinite. It gives us a better observation inside the region from which information has reached us. For the rest of the journey, that is the useful rule to keep nearby. Whenever a boundary appears, we can ask what mechanism creates it, what kind of information it limits, and whether crossing it would require a better instrument or something that no instrument can change. Once those questions are kept separate, the scale of the universe becomes easier to discuss without pretending that every horizon is a wall. That galaxy matters because it pushes the confirmed galaxy record into an earlier era. It tells us that luminous structure existed very early, but it does not measure the full size of the universe. A spectrum can establish when a source emitted the light we receive. It cannot by itself tell us how far space continues beyond every region able to communicate with us. Ordinary experience encourages us to merge visibility with size. Reaching the end of a valley or a city tells you something about the boundary of the place itself. Cosmology gives us no comparable outside viewpoint, so the farthest signal we receive and the total extent of space have to be treated separately. All we ever receive are signals arriving here. That point is worth keeping in view. Every astronomical measurement begins with information that arrives here. No observatory can stand outside the universe and take a portrait of the whole system from a comfortable distance. Every measurement begins inside it, with light entering a detector, a spectrum being measured, and an inference being built from those arrivals. Cosmology therefore works from arrivals, using ancient information that has crossed expanding space to reconstruct a history we cannot inspect from outside. And Webb is one of the finest instruments ever made for receiving those deliveries. The record arrives as a faint patch of light rather than a visible boundary. Humans built and launched the telescope, its detector collected the signal, spectroscopy fixed the redshift, and the frontier of confirmed galaxy observations moved farther back in cosmic time. Once that frontier moves, the phrase far away needs more care. In astronomy, it can refer to distance, look-back time, redshift, or the limits of a particular observation, and those meanings have to be separated before the size question can be answered responsibly. The phrase far away seems simple until astronomy asks us to use it precisely. If you look at the moon tonight, you are not seeing the moon exactly as it is at this instant. You are seeing light that left it a little more than a second ago. The delay is too small to matter in ordinary life, so we usually ignore it. The moon looks present because the difference between now and a little over 1 second ago is almost meaningless to us. The sun makes the same idea easier to feel. Its light takes a little more than 8 minutes to reach Earth, which means every sunrise is already an image from the past. If something changed on the surface of the sun at this moment, Earth would continue receiving the older light for several minutes before the change became visible here. Move beyond the solar system and the delay grows quickly. The nearest stars are years behind the moment we call now. A galaxy millions of light years away appears as it was millions of years ago. And when a telescope receives light that has been traveling for billions of years, distance begins to behave almost like a historical archive. Looking farther outward also means looking farther backward. NASA often uses this idea when explaining how James Webb sees the early universe. Light takes time to cross space, so a distant galaxy is never presented to us in its current condition. What reaches the telescope is an older version of that galaxy, carried by photons that left it long before the Earth, the Sun, or even the Milky Way looked the way they do today. This is why a telescope can function almost like a time machine without violating anything in physics. It does not send us backward. It collects information that has spent a very long time coming forward. With MOM-Z14, that journey lasted about 13.5 billion years. The galaxy appears to us during a period only about 280 million years after the Big Bang. When Webb detects it, the telescope is not seeing a galaxy sitting 13.5 billion light years away. It is receiving light that departed when the universe was extremely young, and then crossed a universe that continued changing throughout the entire journey. That last part is where ordinary intuition begins to fail. If space remained perfectly static while light traveled through it, distance would be easier to describe. A photon could leave a galaxy, move through an unchanging distance, and arrive after a travel time that translated neatly into the separation between source and observer. A journey lasting 10 billion years would correspond naturally to a path 10 billion light-years long. But the universe did not remain still while the photon traveled. The space between distant galaxies expanded. The light kept moving, but the geometry through which it moved was changing as well. During its journey, the wavelength of the light was stretched along with the expanding universe. This is cosmological redshift, and it is one of the basic measurements astronomers use when they study very distant galaxies. The word redshift can make the process sound as though the galaxy became redder with distance, but the measurement is more useful than a change of color. Atoms produce recognizable patterns in light. Certain wavelengths are associated with particular transitions in particular atoms, and those patterns appear shifted toward longer wavelengths. When the same pattern appears how much stretching occurred, astronomers can measure how much stretching occurred. For nearby galaxies, the redshift can be relatively modest. For MOMZ14, the shift is extreme. Webb's near-infrared spectrograph measured a cosmological redshift of 14.44. Light that began its journey at much shorter wavelengths has been stretched enormously during the time it crossed expanding space. So when astronomers say that a galaxy is very far away, several different quantities sit inside the sentence. There is the travel time of the light. There is the age of the universe when that light was emitted. There is the redshift measured when the light arrives. And there is the distance between us and the region that emitted the light, a distance that cannot always be described by multiplying the light travel time by the speed of light, because the universe expanded while the journey was taking place. These quantities are related, but they are not interchangeable. That distinction matters enormously when we begin asking how large the observable universe is. A galaxy can appear to us as it existed more than 13 billion years ago, without implying that its present distance from us must be only 13 billion light-years. During those billions of years, the universe expanded, and regions that were much closer together when the photon began traveling can now be much farther apart. There is no need to imagine galaxies racing through a fixed emptiness like fragments from an explosion. On sufficiently large scales, cosmological expansion is described as a change in the distance between locations as the universe evolves. The light moves locally through space at the speed of light, while the scale of the space it is crossing changes over cosmic time. This is why phrases like 13 billion years ago and 13 billion light-years away should not be treated as automatic synonyms when discussing the distant universe. They answer different questions. One asks when the light began its journey. Another asks how we define distance across an evolving cosmos. And the farther away we look, the more important that distinction becomes. It may help to imagine drawing dots on the surface of a soft sheet and then slowly stretching the sheet while a tiny traveler moves from one dot toward another. The traveler never stops moving toward its destination, but the distance represented by the sheet can change during the journey. The path cannot be understood only from the traveler's speed and travel time unless we also know how the sheet changed. No analogy is perfect here. The universe is not known to be a rubber sheet expanding into some larger room, and cosmological expansion does not require an external space around it, but the image is useful for one narrow reason. It reminds us that the route followed by ancient light has a history of its own. That history is encoded in the light Webb receives. By measuring the spectrum, astronomers are doing more than deciding how distant a galaxy appears. They are placing its light within an evolving cosmic timeline. A very large redshift tells us that the universe has expanded substantially since the light was emitted, which allows cosmological models to connect the observation with an era in the early universe. This is also why records for the most distant galaxy are usually expressed in terms of redshift and cosmic age, rather than as one simple number of light-years. At these distances, a single distance number can hide more than it reveals, unless we specify exactly what kind of distance we mean. And now the word edge becomes even more slippery. If we say MOMZ14 is near the present frontier of galaxy observation, we are talking about one kind of frontier. It is a limit defined partly by the brightness of early galaxies, partly by the wavelengths reaching us, partly by the sensitivity of our instruments, and partly by how early in cosmic history galaxies had enough time to form. A better telescope may move that frontier, as Webb already has, and a future instrument may move it again. But another boundary is waiting behind this one, and unlike the sensitivity of a telescope, it cannot be overcome by polishing a larger mirror. There is a time in the early universe beyond which ordinary light cannot show us a clear picture at all. Telescope size and signal brightness are not the obstacle here, because the universe itself was once opaque. For hundreds of thousands of years after the Big Bang, photons could not travel freely across great distances. Matter and light interacted constantly inside a hot plasma, and the cosmos behaved more like a glowing fog than the transparent space we know today. Only after the universe expanded and cooled enough for electrons and atomic nuclei to combine did light begin traveling freely across enormous distances. That ancient light is still here. It surrounds us from every direction as the cosmic microwave background, a faint afterglow from a universe only about 380,000 years old. And once we reach that boundary, the meaning of seeing farther changes again. James Webb can search for galaxies astonishingly close to cosmic dawn, but even Webb does not continue looking backward through ordinary light until it reaches the Big Bang. Long before the first galaxies formed, the universe placed another kind of horizon in front of us. So the next question is no longer how capable a telescope can become. It is what happens when the thing limiting our view is not the telescope at all. Before recombination, building a better telescope would not have helped us see much farther back using ordinary light. The limitation came from the physical state of the early universe rather than from the distance alone. Today, the space between stars is so empty that a photon can travel for millions or billions of years without striking anything. This is so familiar to astronomy that it is easy to forget how unusual it would have seemed in the earliest universe. Back then, space was filled with a hot, dense mixture of particles and radiation. Electrons moved freely instead of being bound into atoms, and photons repeatedly scattered from those charged particles. Light existed everywhere, but it could not go very far. If you could somehow place an observer inside that early plasma, there would be no dark sky filled with distant objects. There would not yet be stars or galaxies to look at anyway, but even if there had been, light from them could not have crossed the surrounding material cleanly. Photons would scatter again and again, changing direction, before they could carry a clear image across the cosmos. The comparison with fog is useful as long as we remember that this was not ordinary water vapor hanging in empty space. The fog was the universe in its early physical state. Matter and radiation were so closely coupled that light could not yet travel freely over enormous distances. Expansion changed those conditions because the universe cooled as it grew. Eventually, at an age of about 380,000 years, temperatures had fallen enough for electrons to become bound to atomic nuclei. Hydrogen could remain neutral instead of being continuously ionized by the surrounding heat. With far fewer free electrons available to scatter photons, the universe became transparent. Light that had spent its existence constantly interacting with matter could finally travel. Some of that light is arriving at Earth right now. We call it the cosmic microwave background. The name makes it sound like a distant object, perhaps something sitting behind the galaxies, but that is not really what we observe. The cosmic microwave background appears across the entire sky. No matter which direction a microwave telescope points after foreground emission is accounted for, there is ancient radiation coming toward us from the early universe. It is the oldest electromagnetic light we can directly observe. Yet even this oldest light is not a picture of the Big Bang itself. That distinction matters. The cosmic microwave background shows the universe at the era when freely traveling light first became available to us. Everything before that lies behind an electromagnetic fog, at least if our method is to use freely traveling photons as messengers. So there is another boundary here, but it is unlike the boundary James Webb is approaching when it finds earlier and earlier galaxies. Webb's galaxy frontier depends on what objects existed, how bright they were, what wavelengths their light has been stretched into, and whether our instruments are sensitive enough to measure them. The cosmic microwave background boundary has a deeper physical cause. Before the universe became transparent, light could not preserve a clean view across cosmic distances. Neither a larger mirror nor a colder detector changes that physical history and greater sensitivity cannot make the early plasma transparent. This gives us another meaning of an edge. The first was an instrumental and astrophysical frontier, the earliest galaxies we can currently identify. The second is a boundary written into the history of light itself. And even now, it is easy to imagine this second boundary incorrectly. When we see maps of the cosmic microwave background, they are often displayed as oval projections covered in red, orange, blue, and yellow patches. The colors show tiny temperature differences across the sky. Those maps can give the impression that we are looking at a distant shell surrounding the universe, almost like the inner surface of an enormous cosmic room with Earth near its center. But Earth is not at a privileged central location. The shell-like appearance comes from our position as observers. Light has had a finite amount of time to reach us. In every direction, we receive cosmic microwave background photons that last scattered as neutral atoms formed and free electron scattering fell sharply. Those photons come from regions that were located at just the right places for their light to arrive here now. Taken together, those directions form something astronomers often describe as a surface of last scattering. The phrase surface can be misleading if we picture a material wall. There is no solid sphere out there. There is no ancient membrane waiting for a spacecraft to collide with it. It is better to think of the surface as a boundary in our past light history. It marks the places and times from which the photons reaching us today last scattered before beginning the long journey that eventually ended in our instruments. An observer located in another galaxy would also see a cosmic microwave background around them. Their visible surface of last scattering would be centered on their location, because their light history would be different from ours. This is a subtle point, but it removes one of the oldest intuitive traps in cosmology. Whenever we look deeply enough, we seem to be placed at the center of what we can observe. That does not mean we occupy the center of the universe. It means observation is always centered on the observer. Cosmology takes that ordinary fact and extends it across billions of light years and almost the entire age of the universe. The cosmic microwave background surrounds us because we are receiving ancient light from every direction. Its apparent sphere tells us about our observable past, not about a physical outer skin wrapped around everything that exists. And the light itself has changed greatly during its journey. When those photons last scattered, the universe was thousands of degrees hotter than the cosmic background appears today. Expansion stretched their wavelengths as space evolved. Radiation that once belonged to a much hotter environment has been shifted into the microwave region, leaving a background with an average temperature only a few degrees above absolute zero. The universe did not become colder in the ordinary sense of an object sitting outside and losing heat to a surrounding room. There is no colder room outside the universe required for this to happen. The radiation cooled as cosmic expansion stretched its wavelengths and reduced the energy carried by individual photons. So the faint microwave glow around us is ancient in two ways. Its photons have been traveling almost since the beginning of the transparent universe, and their present wavelengths carry the accumulated effect of cosmic expansion during that journey. A map of that glow is therefore both a picture and a record. The picture shows tiny differences in temperature across the young universe. The record preserves information about regions that were slightly denser or slightly less dense than others, variations that later participated in the formation of stars, galaxies, clusters, and the immense structure surrounding us today. For the size question, the more useful connection is straightforward. James Webb can keep improving our view of the period after recombination. It can find earlier galaxies. It can search deeper into cosmic dawn. It can tell us how quickly the first luminous structures assembled and how those structures transformed the gas around them. What it cannot do is turn the cosmic microwave background into a transparent window by being more capable. That is a different limit. And because it is a different limit, the phrase "farther than Webb can see" begins to split in two. There are things Webb cannot see because they are too faint, too redshifted, or outside the particular capabilities of its instruments. Then there are epochs that ordinary electromagnetic observation cannot reveal directly, because the photons from those epochs did not travel freely toward us. Those limitations come from different causes. One can move as technology changes, while the other is set by the physical history of the universe. And neither one tells us that we have found the outer edge of space. We have now moved far beyond the earliest galaxy to the oldest electromagnetic image available to us, yet none of these observations has produced a spatial warp. We have found limits in time and transparency without finding the end of the universe. The next boundary is larger than both of these, because it asks us to stop thinking only about which objects or epochs our telescopes can detect, and instead ask which parts of the universe could have sent information that reaches us by now. That boundary is what turns a very large universe into an observable one. Once we stop treating the oldest thing we can see as the edge of everything that exists, another phrase becomes available to us, and this one is much more precise. The observable universe. It sounds almost like a synonym for the universe itself, but the extra word is doing nearly all of the work. Observable does not mean the part our present telescopes happen to be sensitive enough to photograph. It does not mean the region James Webb can reach, or the part that appears on our deepest images. In cosmology, the idea is more fundamental. It describes the region from which information could have reached us during the history of the universe. That makes the boundary very different from the galaxy frontier we began with. If engineers someday build a telescope far larger than Webb, they may discover galaxies earlier than MOMZ-14. The frontier of known galaxies can move because our instruments improve and because we become better at separating extremely faint signals from everything around them. The boundary of the observable universe is not like that. It exists because information travels at a finite speed, and the universe has a finite age. There has only been so much time for distant signals to arrive here, but somewhere the situation changes. There are locations sufficiently distant that a signal originating there could not yet have reached us, because the journey has not had enough cosmic time to finish. The dividing distance is related to what cosmologists call the particle horizon. It is one of several horizons used in cosmology, and those horizons are easy to confuse because all of them describe limits, but they do not describe the same limit. For now, the particle horizon is the important one. It marks the greatest distance in the cosmological model from which information could have reached an observer by the present time. And this produces a number that seems impossible the first time you hear it. The universe is about 13.8 billion years old, but the present radius associated with the observable universe is commonly given as roughly 46 billion light-years. A diameter, therefore, on the order of 92 billion light-years. If we were working in an ordinary static space, this would make no sense. Light traveling for 13.8 billion years could not cover 46 billion light-years. The arithmetic would fail in a static space, but those photons crossed an expanding universe rather than the present-day distance. A region that is now tens of billions of light-years away was much closer when the ancient light we receive from it began its journey. While that light was traveling toward us, the distance between widely separated regions of the cosmos continued to evolve. So the age of the universe tells us how long the journey could have lasted. The present distance tells us something different. It tells us how far apart those locations are now, according to the distance convention being used in the cosmological model. The two numbers do not have to match. In fact, their failure to match is one of the clearest reminders that cosmic distance cannot always be treated like the distance between two houses on an unchanging road. The road itself has a history. There is another detail here that can sound alarming until it is placed carefully. In an expanding universe, sufficiently distant galaxies can have recession rates greater than the speed of light. This does not mean those galaxies are locally flying through space faster than a nearby beam of light, and it does not mean Einstein's special relativity has failed. The recession comes from the way cosmological distance changes as space expands on very large scales. Light near any observer still moves locally at the speed of light. But there is no requirement in general relativity that the distance between very remote, comoving regions must increase at less than that speed. This distinction is why the universe can grow in a way that ordinary motion through space cannot. It also explains a common misunderstanding about the Hubble sphere. There is a distance at which the recession rate associated with cosmic expansion equals the speed of light. That distance is often called the Hubble radius, and the corresponding surface is sometimes called the Hubble sphere. It is tempting to call that the edge of the observable universe, but it is not. We can receive light from galaxies whose recession rate was greater than the speed of light when that light was emitted, because the expansion history changes the path available to the photon. The Hubble sphere is therefore not a simple wall beyond which observation becomes impossible. The particle horizon and the Hubble sphere answer different questions. One concerns how far information could have reached us during cosmic history. The other is tied to the expansion rate at a particular cosmic time. Keeping them separate saves us from turning one mathematical boundary into a physical wall that is not actually there. And so, by the time we reach the phrase observable universe, something important has happened to our original question. We began by imagining James Webb pushing toward an outer edge. Then the first boundary turned out to be a frontier of galaxies. Behind that came the cosmic microwave background, a boundary related to the early universe becoming transparent. And now we have reached a larger causal boundary, one defined by whether signals can have arrived here by now. Each step feels more fundamental than the last. Yet none has given us what we originally imagined. We still have no wall or outer surface where a telescope could reveal light on one side and non-existence on the other. Instead, we have learned the size of the region that can presently be connected to our observations. That is an extraordinary achievement. A sphere with a present radius of roughly 46 billion light-years is already far beyond anything the human mind evolved to picture. Even light-years stop being helpful at that scale. The numbers become coordinates in an equation more easily than they become distances we can feel. But the number also carries a quiet warning. 46 billion light-years is an estimate for the scale of our observable region under the cosmological model. That number estimates our observable region rather than the entire universe, which could extend beyond the horizon by an amount we do not presently know. And here, for the first time, better telescopes alone begin to lose their authority over the problem. A telescope can collect information that reaches it. It cannot collect information that has never arrived. This creates a distinction between something being difficult to observe and something being causally unavailable to us at the present time. One problem can be attacked with engineering, while the other comes from spacetime itself. James Webb is extraordinarily good at the first problem. Its infrared sensitivity lets it collect ancient light that previous telescopes could not examine in the same way, and every new early galaxy helps refine our picture of cosmic history. But Webb operates inside the same causal structure as everything else near Earth. A future instrument may use a larger mirror, colder detectors, greater sensitivity, or a better observing location, but all of those improvements still operate inside the same causal structure. None of that places it outside our observable universe. It receives the photons that can reach this region of space-time, just as we do. So Webb has a limit, although it is important to understand what kind of limit we mean. Some limits belong specifically to Webb and may be pushed farther by future instruments, while other limits belong to electromagnetic light itself. Different cosmic messengers may tell us about epochs light cannot show directly. And beyond those lies the larger question of causality itself, the boundary created by the finite history of what can reach us. These nested limits are why the title of this story can be true without claiming that the universe is infinite. James Webb has limits that the universe does not necessarily share, and that statement does not prove that space continues forever. It does not prove that the total cosmos is infinite, or even tell us exactly how much larger it might be than the portion we observe. It tells us something narrower and in its own way more unsettling. Our inability to see beyond a horizon is not evidence that there is nothing beyond it. So if observation alone cannot reveal the full extent of the universe directly, cosmologists have to approach the question from another direction. They look at the space we can observe and ask about its geometry. They ask whether space shows positive curvature, negative curvature, or geometry so close to flat that no large-scale curvature has been detected within the precision of our measurements. Because if there is no visible wall to find, perhaps the shape of the space around us can tell us something about how much farther it might continue. If the observable universe is only the region from which information has been able to reach us, then perhaps its shape can tell us something about what continues beyond it. That sounds promising because geometry feels more solid than a horizon. A horizon depends on where the observer stands and how long light has had to travel, while geometry seems to describe the space itself. If we could measure the curvature of the universe precisely enough, perhaps we could infer whether space eventually closes back on itself or continues far beyond the region we can observe. Cosmologists have spent decades trying to make exactly this kind of measurement. And the answer, at least across the scales we can test, is remarkably close to flat. The word flat needs some care here. It does not mean the universe resembles a thin sheet, and it certainly does not mean that stars and galaxies all occupy one plane. A spatially flat universe can still have 3 dimensions. Flatness describes the geometry of space on very large scales, particularly the relationship between distances and angles. On an ordinary flat surface, the angles of a triangle add to 180 degrees. Parallel lines behave in the familiar way. The circumference of a circle is related to its diameter by the number pi. Curved surfaces behave differently. On the surface of a sphere, for example, it is possible to draw a triangle whose angles add to more than 180 degrees. Begin at Earth's North Pole, travel south along one line of longitude until you reach the equator. Move a quarter of the way around the equator, then travel north along another longitude. The resulting triangle can contain 3 right angles. The surface is curved, so the geometry differs from a flat plane. A negatively curved surface would behave in the opposite direction. Triangles could contain less than 180 degrees, and initially parallel paths could separate. Cosmology takes these familiar geometric ideas and extends them into 3-dimensional space. In a positively curved universe, space could behave somewhat like a higher dimensional version of the surface of a sphere. The analogy is imperfect because the sphere we picture is a 2-dimensional surface embedded in a 3-dimensional room, while the curvature of the universe does not require us to imagine an additional external direction into which it bends. Curvature can be an intrinsic property. An observer living entirely within the space can, in principle, measure it without ever seeing the space from outside. A negatively curved universe has a different large-scale geometry, and a spatially flat universe follows the familiar Euclidean relationships on sufficiently large scales. One reason the cosmic microwave background is so valuable is that it gives cosmologists a way to test these possibilities. The young universe contained patterns with characteristic physical scales produced by the interaction of matter and radiation before the cosmic microwave background was released. When astronomers measure how large those patterns appear across the sky, they can compare their apparent angular size with predictions for different geometries. You can imagine placing an object of known size at an enormous distance and asking how large it appears. The answer depends on the object's size, its distance, and the geometry through which its light has traveled. Positive curvature, negative curvature, and flat geometry alter that relationship in different ways. Measurements from the Planck mission have shown strong consistency with the standard cosmological model in which the universe is spatially flat. When Planck data are considered together with other cosmological measurements, the allowed curvature becomes very small. That is one of the reasons illustrations of the universe often describe its large-scale geometry as flat. But this is also where a very tempting conclusion needs to be resisted. Flat does not automatically mean infinite. An infinite flat space is mathematically possible, and it is perhaps the easiest version to picture. Space continues. Travel far enough in any direction and there is always more distance ahead. No outer wall appears because there is no outer wall to reach. But geometry and topology are different questions. Geometry describes local and large-scale relationships involving curvature and distance. Topology asks how the space is connected to itself. A space can be locally flat and still have a finite total volume if its global connections are arranged in the right way. A simple 2-dimensional analogy is the surface of a video game world where leaving the right side causes you to return from the left, while leaving the top brings you back from the bottom. The surface can be represented as flat locally, yet the connections make the total area finite. Three-dimensional versions of such spaces can also be constructed mathematically. This does not mean the universe actually has one of those shapes. It means that measuring curvature extremely close to zero does not by itself prove infinity. And even if the universe is curved slightly, another difficulty remains. Imagine standing on Earth while trying to determine the planet's shape using only a patch of ground a few meters across. At that scale, the surface appears flat. The curvature is too small to notice directly. Expand your measurements to hundreds or thousands of kilometers, and the geometry becomes much easier to detect. The same principle applies in cosmology, although on a scale difficult to imagine. If the universe possesses a curvature radius vastly larger than our observable region, then the patch available to us could look almost perfectly flat even though the entire structure is curved. A tiny section of a very large sphere resembles a plane. This means better measurements can tighten the limits on curvature. But there is a conceptual distinction between saying that no significant curvature has been detected and saying that the total universe has been proven exactly flat. The observational result constrains the patch we can measure. A claim about the exact geometry of the whole universe would go further. And we do not observe the whole of space. That sentence brings us back to the problem we thought geometry might solve. We hoped the shape of the observable universe would reveal the size of the entire universe. Instead, geometry gives us constraints. It tells us which possibilities remain compatible with what we measure. It can tell us that any curvature, if present within the models being tested, must be small enough to have escaped detection at the precision of those observations. But there is no measurement of an outer circumference waiting at the end of the calculation. If the entire universe is infinite, there is no circumference to measure. If it is finite but vastly larger than our observable region, the relevant global features may lie outside the portion of space from which information has reached us. And if space has a global topology that connects distant regions in some unexpected way, identifying that structure would require observational signatures strong enough to appear inside the region we can actually see. The situation is almost the reverse of what the word telescope suggests. James Webb improves our knowledge by seeing more. Cosmology sometimes advances by understanding what additional seeing cannot guarantee. Webb can push the frontier of known galaxies backward in cosmic time. Microwave observatories can measure the ancient radiation released around recombination. Surveys can map galaxies across enormous volumes. Different observations can be combined to estimate expansion, matter content, and spatial curvature with extraordinary precision. Yet after all of that, a very simple possibility remains open. The universe could be much larger than the part available to us. It could be enormously larger, finite on scales we cannot currently determine, or spatially infinite within cosmological models still compatible with the observations. The evidence does not allow us to choose among all of those possibilities merely by pointing a telescope farther into the darkness. And there is something worth noticing about where we have arrived. At the beginning, the most distant confirmed galaxy seemed remote because its light began traveling during a very early cosmic era. Then we moved behind the first galaxies to radiation released around recombination. Then we moved beyond a boundary in time to a boundary in causality, the observable universe itself. Now even that enormous sphere has become only the patch on which we can perform our geometry. Each time we thought we were approaching the whole, another distinction appeared. The farthest galaxy turned out not to be the farthest light. The oldest light was not a physical wall, and the observable horizon was not a demonstrated edge of existence. And near-flat geometry does not give us a ruler long enough to measure whatever may continue beyond the horizon. This is the point where cosmic scale becomes less like a number and more like a problem of knowledge. We can describe the observable region, measure its contents, reconstruct much of its history, and test its geometry. But the total universe does not have to fit inside the portion that has been able to communicate with us. So the question waiting beyond flatness is no longer only how large the universe is. It is whether there are several completely different kinds of universe, finite, infinite, simply connected in the technical topological sense, or connected back through themselves in ways we cannot easily picture, that could all produce an observable region remarkably similar to the one surrounding us. If that is possible, then there may be no single observation that reveals the whole shape at once. There may only be clues left inside our patch of the cosmos, and limits on how much those clues are able to tell us. If the universe extends beyond everything we can observe, then the next question seems unavoidable. What could be there? The safest answer is also the least dramatic, because we do not know. There may be more of the same large-scale universe we already see, more galaxies, more clusters, more enormous regions of nearly empty space, all continuing beyond the distance from which light has had time to reach us. Nothing about crossing our observable horizon requires the laws of physics to change. The horizon marks a limit in our access to information, so a region can lie beyond it without being exotic in any other sense. But once we allow space to continue beyond what we can observe, several very different possibilities become compatible with the same local view. The universe could be infinite, or it could be finite while still lacking any boundary a traveler could reach. That final possibility feels contradictory, only because everyday objects teach us to associate finite size with boundaries. Tables have edges, rooms have walls, and islands eventually meet the sea. So everyday objects train us to expect finite things to end at a boundary. If something occupies a limited amount of space, we expect there to be a place where it stops. Geometry does not always work that way. Earth's surface gives us the familiar example. Its area is finite, yet someone walking along the surface does not encounter an edge where the planet suddenly ends. Given enough time and ignoring oceans and obstacles, a traveler could continue in one direction and eventually return to where the journey began. The surface is finite because it contains a limited area. It is unbounded because there is no edge on the surface itself. The three-dimensional universe could, in principle, possess an analogous property, although the possible geometries and topologies are richer than the two-dimensional surface of a sphere. And this is where the distinction from the previous section becomes useful. Curvature describes geometry, while topology describes how a space is connected, and a flat rectangular sheet gives a simple way to separate those ideas. Now locally, the sheet had a something leave flat right side. It reappears through the left, and whenever it leaves through the top, it reappears through the bottom. The sheet can still behave locally as a flat surface, yet its global connections have changed, can still behave. Mathematicians can represent this kind of identification using a torus. For cosmology, the useful idea is not that the universe must literally resemble the rubber ring we call a donut. That picture can be misleading because it shows a two-dimensional surface bent through a larger three-dimensional space. The deeper point is that a space can have flat local geometry while still being finite because different locations are globally connected. Three-dimensional versions of this idea exist. A commonly studied example is a three-torus. One way to imagine it is to begin with a cube and identify each pair of opposite faces. Leave through one face and, in the mathematical description, you return through the opposite face. Do the same in any of the three spatial directions, and the space can be finite while having no boundary where a traveler would encounter an end. Again, this is a possible topology, not a claim about the actual shape of our universe. What makes the possibility scientifically interesting is that a small enough multiply-connected universe could leave evidence. Light could potentially reach us along more than one path. If space wrapped around on a scale contained within our observable region, the same physical object might, in principle, appear in different directions, because its light had traveled through different routes through the topology. The cosmic microwave background offers an even more systematic place to look. The surface of last scattering surrounds our observable past. If the topology of space caused that surface to intersect itself in the right way from our observational perspective, different circles in the microwave sky could contain matching patterns because they would correspond to the same physical regions seen along different paths. This is the idea behind searches for matched circles in the cosmic microwave background. Planck researchers searched for signatures of several non-trivial topologies, including flat toroidal possibilities. They did not find evidence for a compact topology on scales small enough to produce the patterns they were searching for. That result matters, but it does not convert the entire universe into a proven infinite space. It tells us that certain compact arrangements below certain scales are inconsistent with the observations. A topology much larger than the observable region could remain invisible to this method. This leaves open a possibility. The entire universe might be finite, perhaps even vastly finite, while the observable part is too small to reveal how the whole is connected. And there is another possibility that is conceptually simpler. Space may continue without end. If the spatial universe is infinite, then our observable sphere would occupy a finite region inside an unbounded expanse. No matter how large the observable universe becomes with cosmic time, assuming the relevant signals can eventually reach us, there would always be more space beyond any finite horizon. Yet observations from inside a finite patch cannot establish that conclusion merely because no curvature or repetition has been detected. The data can tell us that the observable region is consistent with certain geometries. They can place lower limits on some possible compact scales. They can eliminate models whose predicted patterns should already have appeared in the sky. But there is a difference between eliminating a small finite universe and proving an infinite one. A universe can be much larger than its observable portion without being infinite. Our observational patch is enormous, containing the cosmic microwave background, vast galaxy surveys, and a record that reaches back almost to the beginning of the transparent universe. And still, from the perspective of whatever the total universe may be, that patch could represent only a small part. We do not know the ratio. That uncertainty is more interesting than assigning an invented number to it. There is no verified measurement saying that the entire universe is twice the diameter of the observable universe, or 1,000 times larger, or 1,000,000,000,000 times larger. Numbers like those sometimes appear in casual explanations because the mind prefers a scale it can repeat. Cosmology does not currently give us one reliable total diameter to recite. What we have instead are constraints and possibilities. Certain compact topologies can be tested because they would leave patterns within our observable sky. Certain curvature values can be constrained because they would change measurable relationships in the cosmic microwave background and other observations. A sufficiently small repeating universe should reveal itself. So far, the relevant Planck searches have not found that evidence. But a global structure beyond the scale available to observation remains a different problem. So when we return once more to James Webb, its role becomes clearer. Webb can reveal galaxies that were previously beyond our observational reach. A future observatory may reveal earlier galaxies still. Other instruments can map the microwave background more precisely, survey enormous distributions of galaxies, or search for subtle signatures of global geometry. Each improvement enlarges the body of evidence, but none allows us to move the observatory outside the entire system and turn around. There is no known external platform from which the universe can be photographed as a complete object. Every map remains a map constructed from inside, and so the darkness beyond the observable horizon should not be imagined as empty black space that astronomers have somehow confirmed to contain nothing. The darkness in that picture represents missing information. There could be more galaxies there. There could be structures so distant that no signal from them has reached us. There could be regions similar to ours extending across an enormous but finite space. Or the continuation could have no spatial end. The observations we possess do not yet choose among all of those possibilities. That is where the original question changes from asking how large the universe is to asking what a measurement of its global form would actually require. What would it even mean to measure the size of something when the evidence needed to determine its global form may lie permanently outside the region capable of communicating with us? Because there is one more complication waiting inside the word horizon. So far, we have been discussing the limit of what could have reached us by the present. But an expanding universe also raises a different question. There may be places whose light has not reached us yet, and there may be places from which a signal sent now will never reach us, even if we wait for an arbitrarily long time. The difference between those two statements leads to another horizon, one that does not describe our past. It describes which parts of the universe can ever share a future with us. By this point, the word edge has split into several different things. The oldest electromagnetic light, the particle horizon of what has been able to reach us, and the still unknown total extent of space. They arise from different mechanisms, so there is no single final shell that Webb or any future telescope is steadily approaching. From here onward, the deeper question is not where one edge sits, but which information each boundary allows us to receive. The horizon we have been discussing so far is a boundary made by the past. There has been a finite amount of cosmic time. Light travels at a finite speed, and so only a limited region could have sent information that reaches us by now. That is the basic idea behind the particle horizon and the observable universe. But cosmology contains another horizon that points in the opposite direction. It is a boundary made by the future. To understand it, imagine a galaxy so distant that we can still receive ancient light from it today. The photons entering our telescopes may have left that galaxy billions of years ago, when the separation between us was much smaller than it is now. That ancient light still makes the galaxy visible enough for us to photograph it, measure its spectrum, and learn about the source when the photons began their journey. And yet it is possible in an accelerating universe for a signal emitted by that same distant region at a sufficiently late time never to reach us. Ancient light from the region can arrive even if light emitted much later never does. This sounds contradictory, until we remember that the path between two distant locations does not remain fixed while the signal is traveling. The universe is expanding, and observations indicate that this expansion is currently accelerating. In the standard cosmological picture, dark energy is the name given to whatever is responsible for that acceleration, although its physical nature remains unknown. If that accelerated expansion continues in the way described by the standard model, there is a cosmological event horizon. The event horizon is not the same as the particle horizon. The particle horizon asks how far information could have traveled to us during the history that has already happened. The event horizon asks a different question. From which regions could a signal ever reach us, even if we allow the universe to continue for an arbitrarily long time? That single change from has reached us to can ever reach us turns the horizon from a record of the past into a statement about possible futures. And it produces one of the quietest forms of separation in cosmology. There can be a galaxy whose ancient light we continue to receive for a very long time, while the later history of that galaxy becomes inaccessible to us. Nothing dramatic has to happen at the boundary. Nothing like a wall or flash marks the boundary, and a galaxy does not vanish at one precise visible moment because it crosses a line on a cosmological diagram. Instead, the information available to us becomes increasingly old and increasingly redshifted. Light emitted later must cross an expanding distance, and in a universe whose accelerated expansion persists, there are events whose signals never complete the journey to us. The easiest mistake would be to imagine the event horizon as a second version of a black hole horizon surrounding Earth. The analogy is limited. Both involve causal boundaries, but their physical situations are different. A black hole event horizon is associated with the strongly curved spacetime around a collapsed object. A cosmological event horizon arises from the large-scale evolution of the universe. The useful common idea is causality. On one side of a relevant causal boundary, signals can reach a particular observer. Beyond it, certain signals cannot. That does not mean the distant region has ceased to exist. It means its future can become disconnected from ours. There is something almost strange about using the word disconnected here, because gravity, light, and information usually make the universe feel like a single continuous place. We see galaxies across immense distances precisely because something from them has reached us. The photons reaching us prove that a causal connection existed for those emissions, but that does not guarantee the same connection for every later event. And that last phrase introduces an important uncertainty. We observe that cosmic expansion is accelerating now. We have a highly successful standard model in which a cosmological constant produces continued acceleration. But the underlying nature of dark energy is still unknown. A true cosmological event horizon depends on what the universe does indefinitely far into the future. If dark energy behaves like a cosmological constant forever, the long-term causal structure has one form. If the physics responsible for acceleration changes, then the distant future could be different. So the event horizon is not something we should describe as though astronomers have traveled forward an infinite amount of time and photographed it. It is a consequence of a model for cosmic evolution. This makes it different from seeing MOM-Z14 in a Webb spectrum or mapping the cosmic microwave background across the sky. Those are observations reaching our detectors now. The future event horizon is something inferred from the way spacetime evolves if the relevant model remains valid. That difference keeps the future claim tied to the model rather than to a direct observation. For the moment, though, suppose the standard picture is approximately right and accelerated expansion persists. Then the future universe slowly changes character. Galaxies that are gravitationally bound together can remain together. The Milky Way and its local gravitational environment do not get stretched apart by ordinary cosmic expansion in the way widely separated unbound regions do. Across larger scales, remote galaxies continue to recede, their light becomes increasingly redshifted, and their signals arrive with less energy over longer intervals. And over extraordinarily long times, more of the distant universe passes beyond what future observers can receive new information from. The accessible universe can become more isolated without the total universe becoming physically smaller, even while the amount of space continues increasing. The total universe could remain vastly larger than anything we have ever observed. But the region from which fresh information can eventually reach a particular observer can be limited by the future expansion of spacetime. Our cosmos can therefore become larger, while the portion that remains causally available becomes, in an informational sense, more restricted. The distinction also explains why the word observable can mean different things depending on the time being discussed. There is the universe observable to us now. There is the larger collection of events whose signals may reach us someday. And there are regions whose future events may never become part of our observable history, even though we can currently see ancient light from objects associated with those regions. No single sphere captures every one of these ideas. This is why cosmologists are careful with the vocabulary of horizons. The Hubble sphere is not automatically the particle horizon. The particle horizon is not the event horizon. The cosmic microwave background is not the edge of space. And Webb's most distant galaxy is not the edge of the observable universe. They are different boundaries created by different pieces of physics. Placed together, they begin to reveal why the simple question, how far can we see, contains more than one answer. But they also reveal something else. The past and the future do not give us symmetrical access to the cosmos. When we look outward tonight, we can receive messages that began billions of years ago. In that sense, the sky is filled with preserved histories. A distant galaxy can show us an ancient chapter because the light from that chapter happened to begin its journey early enough. Its later chapters do not automatically belong to us. There may be no telescope capable of recovering information that never reaches our region of space-time. This is a different kind of limitation from weakness, noise, resolution, or sensitivity. Technology can improve a detector. Technology cannot force an absent photon to arrive. Its limit is not that another telescope will someday be larger. Webb exists inside a universe with causal boundaries. Every future observatory will. However advanced an instrument becomes, it can only study information capable of reaching its location. The mirror, wavelength, or cosmic messenger may change, but every observation still requires information to reach the instrument. And now the question of the universe's total size acquires a second difficulty. The first difficulty came from the past. There are regions whose light has not reached us yet. The second comes from the future. Depending on cosmic evolution, there are events whose information may never reach us at all. Between those two limits sits the observable world we spend our lives trying to understand. This is why the universe may be much larger than anything James Webb can reveal without Webb having failed in any meaningful sense. The telescope is doing exactly what it was built to do. It collects what arrives. The deeper mystery is how much reality never has to arrive here. If these quiet journeys through cosmology help you settle in at night, you can subscribe, and we will keep making more of them. The confusion begins because we use the same spatial language for all of them. We keep using words such as farther, deeper, beyond, and edge. Those words work beautifully when we are navigating a landscape. They become less reliable when the thing we are describing is a history of information moving through an evolving space-time. A better mental picture begins with a single event. Imagine yourself here tonight receiving one photon, perhaps as it enters the primary mirror of a telescope. Perhaps it lands on a detector after traveling through the universe for billions of years. That photon has a history. Trace its path backward and you move toward the place and time where it began its journey. Trace the histories of every photon arriving from every direction, and you begin to build a region of space-time rather than a simple sphere of present-day objects. Physicists describe this using a past light cone. The cone is not a material surface surrounding the telescope. On a space-time diagram, its boundary is traced by light paths that could arrive at the observing event, while events inside the cone could have influenced that observer by slower signals as well. The farther down the cone we look, the farther back in time the events must lie if their information is reaching us now. This is why an observational map can look spherical, even though the underlying object is really a causal history. The apparent outer layer belongs to the set of signals arriving at one place and one time, not to a shell that every observer in the universe would identify as the same physical wall. The name comes from the way the geometry can be drawn on a diagram. Time runs in one direction on the page, space in another, and the possible paths of light form boundaries around the events that could have influenced the observer. The drawing is only a representation, but the idea underneath it is essential. When we look deeply into space, we are also looking down our own past light cone. The distant galaxies in a Webb image are therefore not arranged before us as they all exist at one universal present moment. We see each one at a different stage of its history, because its light required a different amount of time to arrive. A nearby galaxy appears relatively recent. A more distant galaxy appears further in the past. MOMZ 14 appears during an exceptionally early stage of cosmic history. The cosmic microwave background appears earlier still. So a deep image of the universe is already something stranger than a photograph of an enormous room. A deep image collects different times into one observation, because the detector receives the signals now, even though the events that produced them happened at different moments in the past. This is one reason the familiar illustrations of the observable universe have to be treated carefully. A diagram may show Earth in the center, nearby galaxies around it, older galaxies farther out, the cosmic microwave background near the exterior, and perhaps some additional region representing whatever lies beyond observation. The diagram can be useful, but if we unconsciously turn it into a literal photograph of the universe at one moment, it creates a problem. The outer regions look young because we see them when they were young. That does not mean those locations are frozen in the early universe today. Their histories continued after the light we are currently receiving left them. What happened later may already exist in the history of those regions, while the information carrying those later events is still traveling toward us. Or for sufficiently distant future events in an eternally accelerating cosmology, some of that information may never arrive at all. The universe we see is therefore shaped partly by the universe itself, and partly by the causal path through which we are allowed to see it. Now imagine something impossible. Suppose we could place a second observer billions of light years from Earth and somehow compare our observations instantly, ignoring for a moment the fact that instant communication across that distance is not available to us. That observer would occupy the center of a different observable region. They would have their own past light cone. Some events visible to them would also be visible to us. Others would not yet have entered our observable history. And some events visible from Earth might occupy a different relationship to their horizon. Move the observer again and the observable region moves again. There is no single privileged point that carries the one correct sphere. This should feel familiar after our earlier discussion of the cosmic microwave background. The apparent sphere of last scattering is centered on the observer because it describes the ancient photons reaching that observer now. The same principle extends more broadly. An observational horizon tells us about the relationship between an observer and space-time. It does not establish that the observer occupies the geometric center of everything that exists. If the universe extends far beyond our observable region, then somewhere beyond our horizon there could be observers for whom Earth lies near the edge of what they can see. From their perspective, their own location would appear central to the observable cosmos. Neither observer would be standing at the center of the entire universe. They would be standing at the center of their own observational history. Once this settles in, the phrase edge of the observable universe becomes easier to hear correctly. The edge belongs to the word observable. It does not automatically belong to the word universe. This also explains why we cannot wait for Webb to reach farther and expect the uncertainty to disappear. Waiting changes which signals can arrive, while better technology and different cosmic messengers change which arriving signals we can detect. But none of those improvements transforms our viewpoint into an external one. We remain inside the space-time being measured. There is no known observational position called outside the universe from which we could turn around, photograph the whole thing, and compare its total diameter with our calculations. Even the phrase outside the universe may not describe a meaningful physical location. If by universe we mean the full space-time described by the cosmological model, then asking what it is expanding into imports the intuition of an ordinary object sitting inside a larger room. General relativity does not require cosmological expansion to work that way. Distances within the universe can change without the universe needing a surrounding empty container. The familiar balloon analogy sometimes helps, provided we use only the part we need. Imagine creatures confined to the two-dimensional surface of a balloon. As the balloon expands, distances measured along the surface increase. The creatures do not need to travel away from some central point on their surface for this to happen. From their internal two-dimensional perspective, every sufficiently distant region can become farther from every other. We, looking at the balloon from outside, can see a third dimension and a center inside it. That part of the analogy should not be carried over to the real universe. The balloon has an exterior because we built the analogy inside a higher dimensional room. Cosmological expansion itself does not tell us that our three-dimensional space sits inside an accessible external space with a center we could visit. The useful lesson is that expansion can be described internally. Measurements made within the geometry can reveal that distances are changing. No cosmic balcony is required. This makes our position both less special and more constrained than intuition first suggests. We are not placed at a privileged center from which the universe radiates outward, but neither are we able to leave the system and obtain the one perspective that would make its global form obvious. Everything we know about the largest scales comes from patterns available inside our observable region. Those clues the microwave sky, galaxy redshifts, the distribution of matter, the measured geometry of space, the history of cosmic expansion, and the paths taken by light. These are extraordinarily rich clues. Together, they have allowed cosmology to reconstruct a history reaching back almost to the beginning of the transparent universe. Yet reconstruction and external inspection are very different things. A person inside a building can learn a remarkable amount about its structure by measuring walls, following corridors, listening for echoes, and mapping every room that can be reached. But if some portion of the building is permanently inaccessible, there may be global properties that remain uncertain from the available measurements alone. The universe makes this problem much more severe because there is no known doorway to an exterior. There may not even be an exterior in the sense the analogy suggests. So we have reached a different form of cosmic vertigo from the one promised by enormous numbers. The strange part is no longer that the observable universe has a radius measured in tens of billions of light years. The strange part is that even a perfect measurement of everything inside our observable region may not necessarily tell us the total spatial extent of everything beyond it. That is why the universe can remain uncertain after the measurements become extremely precise. Precision answers the questions the observable evidence contains. It cannot guarantee that every global question is encoded inside the accessible data. If there is no external viewpoint, and if the observable horizon may hide regions whose information cannot reach us, then what does it actually mean for cosmologists to talk about the universe as a whole? How much of that whole is measured? How much is inferred? And where does a scientifically responsible answer have to stop and say that the information may not be available? Cosmologists talk about the universe as a whole all the time. They calculate its age, describe its expansion, estimate how much ordinary matter it contains, map the dark matter that helps structure galaxies, and build models that follow cosmic history from a hot early state to the enormous web of clusters and voids we see today. Listening to that language, it would be easy to imagine that the whole universe has somehow been placed on a table and measured. Cosmologists do not have that external measurement. Their models begin with the observable part. The remarkable achievement of modern cosmology is that an enormous amount can be inferred from that part, provided certain assumptions continue to agree with what we observe. One of the most important is called the cosmological principle. In its standard form, it says that when the universe is considered on sufficiently large scales, there is no privileged location and no preferred direction built into its overall distribution. Individual places can differ enormously. A galaxy is not the same as a void. The center of the Milky Way is not remotely similar to intergalactic space. A cluster containing thousands of galaxies is nothing like the comparatively empty regions surrounding it. But average over large enough distances, and the expectation is that the universe becomes statistically homogeneous and isotropic. Homogeneous means that its large-scale properties do not depend strongly on where you are. Isotropic means that on those scales, they do not depend strongly on which direction you look. These ideas are related, although they are not identical. And they matter because without something like them, extending our local observations into a model of the broader cosmos would become much more difficult. If the universe changed completely beyond our horizon, with entirely different large-scale properties in regions we cannot observe, then measurements made here would tell us much less about what exists there. The standard cosmological model instead assumes that our observable region is not a uniquely privileged patch. That assumption did not appear because physicists preferred an elegant universe. It is tested against observations. The cosmic microwave background is extraordinarily uniform across the sky once local effects and small fluctuations are accounted for. Those tiny fluctuations matter because they contain the seeds of later structure, but the overall background still shows a young universe that was remarkably similar in different directions. Large galaxy surveys provide another test. Nearby space is full of obvious structure, with galaxies arranged into groups, clusters, filaments, sheets, and voids. Yet when astronomers average over increasingly large scales, the distribution approaches the statistical behavior expected in the standard cosmological picture. This does not mean every test of isotropy and homogeneity has become trivial. Researchers continue looking for departures from the cosmological principle precisely because the assumption is so important. Large-scale anomalies, unusual alignments, galaxy distributions, cosmic dipoles, and other possible deviations are studied because even a small, persistent failure could change the way cosmological observations are interpreted. The cosmological principle remains useful because it is tested rather than protected from testing, and so far the standard large-scale picture continues to fit a wide range of observations. And once that picture is adopted, general relativity allows cosmologists to describe the universe using a family of expanding geometries. The equations do not require us to draw every galaxy individually. Instead, matter and energy can be treated statistically on the largest scales, and the evolution of the cosmic scale can be followed through time. This is how observations made from one small region can become statements about cosmic history. The process is an inference chain built from observed redshifts, the microwave background, characteristic scales in the distribution of matter, and other measurements across cosmic time. We observe supernovae in galaxies across different cosmic epochs. We compare those observations with models describing how an expanding universe containing different forms of matter and energy should behave. Then we ask which versions of the model remain consistent with the data. That is a very different process from directly measuring every part of the universe. A model can describe regions we cannot presently see because the physics that successfully describes the observable region is extended beyond it. This is common in science. Standing on Earth, you do not need to dig into every point inside the planet before constructing a model of its interior. Seismic waves passing through Earth reveal information about regions no person has visited. Astronomers infer the interiors of stars from radiation, oscillations, and physical theory, rather than opening the stars to inspect them. Black holes are understood partly through the behavior of matter and light outside regions from which no direct signal can escape. Inference is not a weaker form of knowledge, because the object cannot be handled directly. But inference always carries conditions. If the assumptions supporting it fail somewhere inaccessible to observation, there may be no immediate way for us to know. That is where cosmology becomes unusual. The scale of the subject means that some assumptions may be extendable far beyond the region that produced the evidence for them. Suppose our observable universe really is representative of a vastly larger whole. Then extending the same large-scale geometry beyond our horizon may be entirely reasonable. Perhaps there are more filaments, more voids, more galaxies, and more regions governed by the same physical laws, continuing across distances for which we do not yet have direct information. But now suppose, only as a logical possibility, that something changes on scales far larger than our observable region. If that change produces no signal capable of reaching us, then it would leave no direct trace in our measurements today. This does not mean we have evidence that such a change occurs. We do not. It means the observable data cannot automatically exclude every imaginable global structure beyond the horizon. That distinction is important because uncertainty can easily be turned into invention. The fact that we cannot observe beyond the horizon does not give us permission to populate those regions with anything we like. There is no scientific basis for saying that completely different laws of physics begin just beyond our view. There is no observation showing a wall, another universe, an outer darkness, or an abrupt change in the nature of space there. The responsible statement is much quieter. Our successful cosmological models extend the regularities we observe. Their success gives us reason to take those extensions seriously. But the regions beyond our causal axis are not directly surveyed territory. This is also why the word theory means something different in science from the way it is often used in ordinary speech. The standard cosmological model is not a casual guess. It combines general relativity with a specific description of the contents and initial conditions of the observable universe, and it survives an enormous number of observational tests. Planck measurements of the cosmic microwave background, for example, fit remarkably well within a relatively simple cosmological model containing ordinary matter, dark matter, and a component associated with accelerated expansion. The fit is informative because many different observations can be explained within the same framework. Yet even a highly successful model is not the same as a photograph of the whole universe. It tells us what follows if the model describes the relevant domain. And cosmology contains places where the model may be extrapolated beyond direct observation, because there is no other way to discuss the whole. There is a gentle irony here. The better our measurements become, the more clearly we can sometimes see the line between measurement and assumption. Precision does not merely increase certainty. It also reveals where the certainty comes from. The age of the observable universe is constrained through a network of measurements and a cosmological model. The geometry is constrained through observations of the microwave background and other cosmic structures. The expansion history is reconstructed from several kinds of astronomical evidence. The large-scale distribution of matter can be mapped over immense regions. But when we ask for the total spatial volume of everything that exists, we move into a question for which the observable region may not contain a unique answer. A universe far larger than our horizon can look one way from inside our patch. A still larger universe can look the same. An infinite universe can also produce a finite observable region around us. And some finite global topologies, provided their characteristic scale lies sufficiently far beyond our accessible region, could avoid producing obvious repetitions inside the sky we observe. The same local evidence can therefore be compatible with more than one global possibility. This is not because the observations are poor. It is because a finite region does not always determine the structure of an entire space. Imagine receiving a single page torn from an enormous book. The language and grammar on that page may be perfectly clear. You can learn the names of characters, infer something about the setting, perhaps even identify the author. But the page does not necessarily tell you whether the complete book contains 200 pages or 2,000. You could study your page with a microscope and become perfectly certain about every drop of ink. The total number of unseen pages would still be a different question. Our situation is vastly richer than that analogy because the observable universe contains an extraordinary amount of information. We do not possess one page. We possess a cosmic volume almost 14 billion years deep in look-back history, filled with radiation, galaxies, chemical elements, gravitational structures, and records of expansion. Still, the principle survives. Perfect knowledge of a part does not always determine the size of the whole, and that may be the first truly inaccessible feature we have encountered tonight. Earlier boundaries could be crossed conceptually. We moved beyond Webb by considering older light. We moved beyond visible galaxies by considering the microwave background. We moved beyond the microwave background by discussing causal horizons and other messengers. But the question of total size may not be waiting behind another observational door. There may be no final telescope that resolves it. There may instead be a range of global universes that remain compatible with every signal capable of entering our observable region. If so, the difficulty is not that humanity has not waited long enough. The difficulty is that the answer may not be encoded in the information available here. That leaves a darker question. How do you distinguish between a universe that is merely larger than you can see and one whose true size can never, even in principle, be recovered from your observable patch? There is an important difference between a question that has not been answered yet and a question whose answer may not be accessible from where we are. Astronomy is filled with the first kind. For centuries, people did not know what stars were made of. Then spectroscopy allowed astronomers to read chemical fingerprints in starlight. We did not know whether planets were common around other stars. Then, increasingly sensitive observations began finding them by the thousands. We did not know what the earliest galaxies looked like. Now James Webb is collecting light from objects that existed near cosmic dawn. In cases like these, ignorance was temporary because the information was already capable of reaching us, and we needed a better way to receive it. The question of the universe's total size may belong to a different category. That does not mean cosmologists have proven that the answer is unknowable. Such a statement would go farther than the evidence allows. Future observations may uncover patterns we have not yet recognized. A new physical theory may connect quantities we currently treat as separate. Measurements of curvature, topology, primordial fluctuations, gravitational waves, or other cosmic messengers may constrain possibilities more tightly than they do today. Science has surprised itself too many times for anyone to declare the investigation finished. But there is a reason the question is unusual. Any evidence we receive must somehow enter our causal region. If a feature of the universe lies permanently beyond every horizon from which information can reach us, and if it leaves no observable imprint inside our region, then the feature cannot be photographed by waiting for a larger telescope. At that point, the problem is no longer sensitivity, but the absence of a message, which becomes clear if we return to cosmic topology. If space repeats on a scale small enough, the repetition can potentially leave signatures inside the cosmic microwave background. The same physical region might contribute patterns along different lines of sight, allowing astronomers to search for correlations that would reveal something about the global connections of space. Planck performed searches of this kind. The absence of convincing evidence allows certain small compact universes to be ruled out. But imagine that the repeating scale, if one exists at all, is vastly larger than our observable region. Then there may be no duplicated structure available inside our sky. The topology can still describe the global universe, even if it leaves no detectable clue inside the portion available to us. Curvature presents a similar problem from another direction. Measurements are consistent with spatial geometry being extremely close to flat on the scales we observe. Combining cosmic microwave background information with other measurements places tight restrictions on how much large-scale curvature can be present within the cosmological framework being tested. But as the permitted curvature becomes smaller, the corresponding curvature scale can become larger. A very gently curved space can look extraordinarily flat across a limited region. So an increasingly precise result saying that our observable patch is close to flat may push the possible scale of global curvature farther away rather than reveal a finite circumference. The measurement becomes better. The whole does not necessarily become measurable. This is an unusual feeling because we are used to precision reducing uncertainty in every direction. Measure a table more carefully and its dimensions become clearer. Map an island more carefully and the coastline becomes more accurate. Observe a planet for longer and its orbit becomes more tightly constrained. Cosmology sometimes gives us a different result. We can become extremely certain about the properties of the observable patch while remaining uncertain about how that patch fits into a much larger structure. The situation can be described without invoking anything exotic. Imagine a perfectly flat floor extending beyond a closed door. You are allowed to measure only the room you occupy. You can test the floor at thousands of locations and find no measurable curvature. You can map every centimeter available to you. You can determine the dimensions of your room with remarkable accuracy. None of those measurements automatically tells you whether the floor continues for 10 more meters, 10 kilometers, or indefinitely beyond the walls if no information from the exterior is permitted to enter. Cosmology is not literally a room with walls, of course. The analogy only isolates the informational difficulty. A precise map of an accessible region does not always contain the global size of the space containing it. Inflation makes the question even more interesting. A leading class of early universe models proposes an extremely brief period of accelerated expansion called inflation. These models were developed in part because inflation can help explain features we observe today, including the remarkable large-scale uniformity and near-flatness of the observable universe. But inflation does not give us a simple tape measure for the entire cosmos. If inflation occurred, it could make the region containing our observable universe vastly larger than the part we can see today. Different inflationary scenarios have different global implications, and observations constrain aspects of those models without presenting us with one measured total diameter for all of space. The near flatness we observe is consistent with inflationary models, but it does not turn the total extent of the universe into a known number. And there is a deeper reason why our visible region can be so informative while remaining incomplete. The laws of physics appear remarkably consistent across the regions we can study. Atoms in distant galaxies leave the same recognizable spectral fingerprints. Gravity shapes large structures in ways that can be modeled across enormous spans of cosmic time. The cosmic microwave background carries statistical patterns that can be analyzed with extraordinary precision. Because these regularities hold across the accessible cosmos, extending the same physics beyond our horizon is a reasonable scientific move. But reasonable extrapolation and direct observation remain different things. If the universe continues far beyond our horizon and remains statistically similar to our observable region, then the standard cosmological picture may describe that unseen continuation extremely well. We cannot point to those regions and say that this particular galaxy, this particular void, or this particular event has been directly measured. There is a quiet discipline in leaving that distinction intact. It prevents uncertainty from turning into spectacle. Beyond the observable universe, we do not have evidence for a black wall. We do not have evidence for a literal boundary where space ends. We do not have evidence that another universe begins 1 meter beyond our horizon. We do not have evidence for an exterior room into which our cosmos is expanding. And we do not have a measurement showing that familiar space continues infinitely far. What we have is a set of models, strong observational constraints inside our accessible region, and a boundary beyond which direct information becomes increasingly difficult or impossible to obtain. That is enough to make the mystery profound without adding anything to it. There is another way to appreciate the problem. Imagine two universes. Inside the first, space continues for an immense but finite distance beyond everything we can observe. Inside the second, space continues without end. Now suppose both universes are arranged so that every event inside our observable region is identical. Suppose the same Milky Way and Sun form, Earth follows the same orbit, the same microwave background reaches our detectors, the same visible galaxies fill the sky, and Webb records exactly the same photons in both universes. From our location at this moment in cosmic history, how would we tell which universe we lived in? If some global feature produced an observable signature, then the two cases would not actually be identical, and the signature could provide a test. But if the difference existed only beyond all possible causal access and left no imprint within our observable domain, then no comparison of the information available here would distinguish them. That is not a failure of intelligence. It follows directly from the way evidence works. To tell two physical possibilities apart, something observable has to differ between them. If nothing available to observation differs, measurement has nothing to choose between. This idea appears throughout physics, but the universe makes it unusually personal because there is nowhere else for the observer to go. We cannot build a second laboratory outside space-time. We cannot repeat the universe with slightly different initial conditions. We cannot move far enough away to place the cosmos inside our field of view. There is only the universe available to us, observed from locations inside it, at a particular stage of its history. And yet this limitation has not prevented us from learning an astonishing amount. This part is easy to lose when discussing horizons. The observable universe is not a small consolation prize. It contains a record extending across almost the entire age of cosmic history. We can observe galaxies at many stages of development. We can read the chemical composition of ancient gas. We can map radiation from a time before any star existed. We can reconstruct the growth of structure from tiny early density variations. We can measure the expansion of the universe and test the geometry of space. We can watch gravity bend light that crossed billions of years before reaching us. And now Webb is extending one of those records toward a time when the first galaxies were only beginning to turn on. So the existence of an information boundary does not diminish astronomy. It explains what kind of achievement astronomy really is. We are building a history of the cosmos using only messages that happen to arrive here. Some of those messages began their journey before Earth existed. Some began before the Sun existed. Some began before the Milky Way had acquired its present form. The oldest electromagnetic message we can see began traveling before stars and galaxies had appeared at all. Each one crossed a universe that was changing as it traveled. Then, for a brief moment in human history, instruments existed that could receive it. Seen this way, James Webb's limit stops looking disappointing. A telescope does not need to reveal the whole universe to change our relationship with it. Webb has already pushed one frontier far enough to show us a cosmos that was forming recognizable structures remarkably early. It has added new pieces to the history between the almost smooth universe seen in the microwave background and the richly structured universe surrounding us now. But perhaps its most useful lesson for this particular question comes from what happens when we ask it to do something no telescope can do. We ask it for the size of everything. And the answer that comes back is not another number. It is a reminder that the farthest object we can observe, the oldest light we can receive, the boundary of causal contact, and the total extent of space are four different ideas. Once those are separated, there is no reason to expect one photograph to contain the answer to all of them. We have now reached the darkest part of the journey, but it is a darkness made mostly of unanswered information rather than danger. Perhaps the universe is finite. Perhaps its global structure closes in a way too large for us to detect. Perhaps space is infinite. Perhaps future physics will reveal a connection that makes one of those possibilities unavoidable. For now, the evidence does not give us a measured outer edge. Return to the tiny yellow blur where we began, OMZ14, a galaxy seen near cosmic dawn. After following the limits of cosmology this far, the better question is what James Webb actually gave us when it brought that ancient light home. The answer is a better view of the difference between an edge and a frontier. That distinction may sound almost too careful after such a long journey, but it changes the meaning of everything we have been looking at. When Webb confirmed MOMZ14, it did not reveal the outer wall of the universe. It revealed a galaxy whose light began traveling toward us during an extremely early stage of cosmic history. That is already enough. There is no need to make the observation larger than it is. A faint galaxy from that early period tells us that matter had already gathered into luminous structures with surprising speed. Its spectrum tells us something about the chemical conditions inside that young system. Its redshift places it deep inside cosmic history. Its light has crossed an expanding universe for roughly 13 an instrument built by a species that did not exist for almost all of that journey. What Webb gives us is a message from one part of the universe's past rather than a photograph of the whole universe. And perhaps the most useful way to understand Webb is to stop imagining it as a machine that looks outward towards some final border. It looks backward. Not because the telescope points toward the past in any ordinary sense, but because distant light takes time to arrive. Every deeper observation reaches us from an earlier chapter. The telescope, therefore, expands our history more directly than it expands our map. Before Webb, astronomers already knew galaxies existed surprisingly early. Hubble had pushed deep into that era, and other observatories had been building the story for years. Webb changed the level of access. Its infrared instruments were designed to collect the heavily redshifted light of very distant galaxies and study it in greater detail. Spectroscopy allows astronomers to move beyond identifying a faint candidate and ask what the light actually contains, where characteristic spectral features have shifted, and how securely the source can be placed in cosmic time. That is how a small blur becomes evidence. The image attracts the eye, while the spectrum carries the measurement needed to place the source in cosmic history. This difference is easy to overlook when we see beautiful Webb photographs. The public experience of the telescope often comes through color, spiral arms, dust clouds, gravitational arcs, and crowded deep fields. But many of the most important questions are answered by something less visually dramatic. Often the decisive evidence is a graph of wavelengths or an emission feature shifted from where laboratory physics says it began. From those quiet measurements, astronomers reconstruct when the light was emitted and what conditions existed in the source. So when a galaxy appears that early in cosmic history, Webb is not showing us a marker placed near the edge of space. It is placing another marker on the timeline. The galaxy frontier can keep moving without the universe itself becoming larger. Suppose a future telescope discovers a galaxy that existed earlier than MOMZ14. Our known universe would not suddenly gain extra space. Our observational history would become deeper. The boundary of known galaxies would shift toward an earlier time because we had found evidence of luminous structure there. The same thing happened when MOMZ14 replaced the previous record holder. The record changed because our access to the universe's past improved. This is what makes record-breaking distance claims so easy to misunderstand. When astronomers say farther in this context, they are often describing an earlier cosmic epoch as well as a greater distance. And because expansion links distance, redshift, and time in ways that ordinary intuition does not, the word farther carries several meanings at once. A telescope record can therefore be real and important without being a measurement of the universe's total scale. That is also why the title we began with needed a quieter answer than a single enormous number. Webb has several practical limits because its mirror has a finite size, its instruments cover particular wavelength ranges, and its detectors have finite sensitivity. Some objects are too faint for it. Some signals lie outside the wavelengths it was designed to study. Earlier than the first luminous sources, there are no galaxies for Webb to photograph. Farther back still, the hot early universe becomes opaque to freely traveling electromagnetic radiation. and beyond all instrumental limits lies the larger causal structure we have been following, the history of which information can reach us at all. The universe may not share Webb's limits. That sentence does not mean the universe is infinite. It means only that the boundary of one instrument, or even the boundary of all electromagnetic observation, should not be mistaken for a demonstrated boundary of existence. There could be more space beyond our observable region. There could be vastly more. The total cosmos might be finite on a scale beyond our present ability to determine, or its spatial extent might be infinite. At the moment, none of those possibilities can be replaced by a measured outer wall. And there is something almost comforting in that. We do not need the universe to fit inside a final diagram before the observations become meaningful. A map can be valuable without containing everything. A history can be profound without beginning on its first possible instant. A telescope can transform astronomy without solving every cosmological question. Webb was never required to reveal the whole. Its achievement is more specific. It allows us to receive older, fainter messages with a clarity that earlier generations did not have. Each one slightly changes the story of how quickly the young universe became complicated. And this brings us back to the little yellow blur that started the journey. When NASA released the image of MOM-Z14, the galaxy itself occupied almost nothing on the screen. The field contains many other objects at different apparent distances and brightnesses, several of them visually more prominent than the record-setting source. Without the annotation, a casual viewer might never know which faint point had pushed the record deeper into cosmic history. There is a strange proportion in that image. The scientific importance of the galaxy is enormous. Its visual footprint is tiny compared with the importance of the measurement. Again and again, the universe hides enormous stories inside very small signals. A slight shift in a spectral line can reveal expansion. Tiny temperature differences in the microwave background can preserve the seeds of later cosmic structure. A faint distortion in the shape of a background galaxy can reveal the gravity of matter we cannot see directly. A brief change in starlight can reveal a planet crossing in front of another sun. That record-setting galaxy is another example of important evidence arriving as a faint signal. Its photons do not tell us everything about the universe. They tell us something true about one very early place. And when thousands, millions, and eventually billions of observations are placed together, the pattern becomes a cosmology. That is how cosmologists approach the whole from inside, by collecting messages rather than stepping outside the system. This perspective gives James Webb a clearer role in the size question. The universe does not present itself to us all at once. It arrives as radiation from one direction, a spectrum from another, microwave photons from almost every direction, and gravitational effects written into the motion of matter and the paths of light. Every piece begins somewhere else and ends here. For a moment, the signal exists in a detector, then it becomes data that can support an inference and eventually a model. And perhaps that is a more faithful image of astronomy than the idea of a telescope staring toward an edge. A telescope waits for whatever information the universe can send to it. At this point, one photon is enough to carry the final idea, a piece of light that began its journey long before Earth existed and crossed a universe that kept expanding beneath it until an observer finally existed at the other end. Imagine that photon arriving tonight. It would not be a beam bright enough to see with your eyes or a dramatic flash crossing the sky, only one small packet of light reaching the end of a journey that began before Earth existed, before the Sun existed, and perhaps before the Milky Way had taken anything like its present form. For almost all of that journey, there was no telescope waiting for it. There was no planet here capable of building one. There was no human language containing words like galaxy, redshift, or observable universe. The photon kept traveling while space expanded and its wavelength stretched as galaxies formed and changed and generations of stars were born and died. Heavy elements accumulated inside generations of stellar interiors. Much later, a young star appeared in one small galaxy, surrounded by a disk of dust and gas. Planets formed around that star, one of them cooled, and oceans eventually collected on its surface. Life changed slowly enough that eventually a species appeared that could notice the night sky and wonder why it was there. The photon was already on its way. By the time humans began recording the motions of planets, it had crossed most of its journey. By the time the first telescopes were pointed toward the sky, it had crossed almost all of it. By the time engineers began designing instruments capable of detecting extremely faint infrared light from the early universe, the photon was already approaching the final part of its path. And then after billions of years it arrived. Perhaps it was absorbed by the detector of a telescope. Perhaps its arrival became one count among many. Perhaps thousands or millions of photons from the same distant source were combined until astronomers could recognize a pattern. The individual photon did not carry a label saying where it came from. The meaning appeared only when enough information was gathered together. Enough photons can produce a spectrum, a wavelength pattern, a redshift, a position in the sky, and a place in cosmic history. This is what it means for the universe to become observable, not that the entire cosmos reveals itself at once. It means information arrives. That may be the simplest way to understand every boundary we have crossed tonight. James Webb has a frontier because only certain signals are bright enough, red enough, and accessible enough for its instruments to measure. The cosmic microwave background marks another frontier because before recombination, ordinary light could not travel freely across the cosmos. The particle horizon marks another because the universe has existed for only a finite amount of time, and information from sufficiently distant regions has not reached us yet. A cosmological event horizon, if the future expansion behaves as the standard model predicts, describes another limit, one involving signals that may never arrive no matter how long the future lasts. These boundaries are real, but they are not the same boundary, and none of them has been shown to be the physical end of space. That is the idea we were trying to reach from the beginning. The observable universe is not everything that exists placed inside an enormous sphere. It is the part of cosmic history that can be connected to us through information. Its boundary is therefore partly a boundary of knowledge, even though we can measure the observable region with high precision, estimate its age, reconstruct how expansion changed over time, and map the microwave background. We can study galaxies at many stages of their development. We can test the geometry of space across enormous scales. We can search for signs that the topology of the universe repeats within the region we can see. We can keep improving every one of those measurements. And still, none of them requires the entire universe to fit inside our horizon. The universe may be finite and vastly larger than the observable part. Its global structure may close in a way that occurs far beyond any scale we can presently detect, or space may continue indefinitely. The evidence available to us does not provide a measured outer wall that settles the question. That uncertainty can feel uncomfortable because the human mind likes complete objects. Planets have radii, continents have coastlines, and buildings have dimensions, so we are used to complete objects that can be assigned an overall size. Even a galaxy, though its boundary is not perfectly sharp, can be described as a structure occupying a particular region of space. We expect that if something exists, there should eventually be a number telling us how large the whole thing is. The universe does not promise us that kind of number. A finite universe would have a total scale of some kind, while an infinite spatial universe would not have a finite total size. And even if a total finite size exists, that size does not have to be recoverable from every location inside it. There is no rule saying reality must arrange itself so that an observer can reconstruct all of it. That may be the quietest lesson of the entire journey. The universe does not owe us a view from outside. We are inside the thing we are trying to understand. Every telescope and detector remains inside the universe, and every equation is tested with information available at some location within it. And somehow from that limited position, we have still learned enough to follow the history of the cosmos backward for almost its entire known age. That is worth holding beside the uncertainty. The limit and the achievement can both be true at once. James Webb does not fail, because it cannot show us the total universe. The cosmic microwave background does not fail, because it cannot reveal an ordinary photograph of the first fraction of cosmic history. Cosmology does not fail because some global possibilities remain difficult to distinguish. Science works by finding the boundary between what the evidence tells us and what we would merely like to know. Sometimes the boundary moves when a new telescope makes a faint signal measurable, reveals a galaxy earlier instruments missed, or turns a prediction into a test. And sometimes the boundary may belong to the structure of the problem itself. The great challenge is knowing which kind we are facing. Return once more to MOMZ14, where the tiny blur is still not the edge of the universe. It is neither the oldest light nor the particle horizon, and it does not measure the total size of space. It is something much more specific. It is a galaxy whose ancient light reached us. And because it reached us, we can know something about a place and time that no human being could ever visit in the form we now observe. The photons carry no explanation of the whole universe. They carry evidence from one small region of it. That evidence joins other galaxies, spectra, microwave photons, gravitational lenses, and patterns in the distribution of matter. Piece by piece, the observable universe becomes less mysterious. But the whole does not necessarily become smaller. Perhaps that is why the deepest images of space can feel so strange. Every improvement in vision gives us more information. And sometimes more information reveals a larger boundary around what information can do. Webb sees farther. So we understand more clearly that farther is not the same as complete. We measure the observable universe more precisely. So we understand more clearly that observable is not the same as entire. When we search for an edge, what the observations give us are horizons, real limits in our relationship with the cosmos, rather than proof that space itself ends there. It is a real feature of our relationship with the cosmos. A horizon is not necessarily where the cosmos ends, it is where a particular kind of knowledge changes, while ancient photons continue arriving tonight. They have crossed billions of years of expanding space and reached this small region at exactly the period when instruments exist that can receive them. Other photons are still traveling. Some will arrive long after everyone alive today is gone. And there may be regions whose messages have not reached us yet, or whose future messages never will. We do not need to fill that silence with imagined walls. We can leave it as silence. James Webb did not carry us to the edge of the universe. It showed us something more useful, how easy it is to mistake the edge of our information for the edge of reality. And somewhere in the darkness, another very old photon continues toward us, carrying only what it can carry from one small part of a universe that has never promised to show us the whole.